people have a tendency to think that analysis is, here's your data, you just analyze it and there's no complexities to it whatsoever. You can just summarize all of these things which have sets of numbers by means and standard deviations and things, and you don't need to worry about it. There's only one correct answer for doing it. So the point of today is to show you that even something as simple as making a table of data and doing a picture actually requires a few cycles and steps of going through your data to see that it's doing what you think it is. So in the previous bit, we sorted out the missing values. So let's just do an analysis. So I want to know what's the average number of calories. So I go to Analyze, I go to Descriptive Statistics and Explore. I press on, I go, I want to look at calories. I want to put plots to be histogram as always. Let's forget the normality tests because I'm starting to get annoyed with them. And it's too much information anyway. Press OK. So we find out these are the key things for summarizing your data. The mean. Now, when you've been summarizing data up until this point, you've recorded the mean and the standard deviation within your tables of data. This is categorically and absolutely wrong. You must not record the mean and the standard deviation. And you're going, but why? That seems sensible, because one tells you where the middle of the data is, and the other tells you the scatter of the data. Now, when you're writing a scientific paper, what you're doing is presenting a set of data for other people. Now, when other people repeat their experiment, they're not going to get exactly the same mean, and they're not going to get exactly the same standard deviation, because their sample is going to be different to your sample. So what they want to know is their mean similar enough to your mean that you can consider the two experiments to be samples which come from the same population, which would give the same result? Or do they come from different populations, in which case one of your samples is not representative compared to the other? They don't come from the same group, from the same population as a whole. Is the estimate from your sample valid or not? So to work that out, I don't need the standard deviation. The standard deviation tells me about the variation of my sample. It does not tell me about the variation between means from different samples. The variation between means of different samples depends on the sample size, and that is called the standard error of the mean. So when you're reporting it, you should report the mean and the standard error. That's as a minimum. So if you see somebody writing a scientific paper and they've reported the mean and the standard deviation, you should start, it should put a red warning light up about that paper, because it means whoever did it doesn't know the slightest thing about statistics and has no clue how to do analysis properly. So this is a warning to say bad science is about to happen. Doesn't mean that it necessarily did happen, but it's a warning that it could happen because this person doesn't know how to do their analysis properly. So I said, mean and standard error is a good way of doing it. A better way of doing it is the mean and the confidence intervals. If your data is not normally distributed, you would do the median instead, which is 110 in this case, and the quartiles. Now, if I go down into look at the box plot here, they're not particularly great in this case because of the way the data is distributed. So it has a few scatters at the end and then a very high density of numbers where they're all practically the same. Your interquartile range is quite narrow, and in this case the median is the same as the third quartile, just because you've got lots and lots of numbers which are practically which are the same number. and then scatter further out. So even doing the median and the quartiles would look a bit strange on this set of data. So let's imagine it is normally distributed. So I do the mean and the confidence intervals. Now, confidence intervals are a bit complicated to understand how they work because it's to do with probability, and we get our head in a mess about probability. So imagine that you live in a town and there's a 10% chance that you have COVID because of infection. You don't 10% have COVID. You either have it or you don't. So up until the moment that your test comes back as positive, there's a 10% chance. But the second you have any confirming evidence, then it becomes certainty. Okay, so the probability goes from chance to certainty. Now, with confidence intervals, it's like that. A 95% confidence interval doesn't mean that there's 95% chance that the real mean is between these two values. It means there's a 95% chance that if I repeat this experiment 100 times, 95 of them will contain the mean between those two values, but 5 of them won't. So there's a 95% chance that this confidence interval is correct, but you can never tell whether you've got one of the correct ones or a bad one. So when somebody else does the experiment, if they get a different result, so their confidence intervals are different to yours and do not overlap, they would say, we've got a different answer, therefore one of us is wrong. That's true, but you can't tell which of the two of you is wrong. You'd have to do a third experiment to find out which one is agreed with. The ideas of probability and confidence intervals do confuse people, so don't hugely worry about it beyond the point of it is only correct to report data with means and confidence intervals, not standard deviations. Right. Anybody want to ask anything up to that point?